Hi, seventh graders. I am Miss Mills, and I'm running this Explain Everything or Quick Time today for you. And our objective today is looking at how we are going to determine the absolute age of fossils using radioactive dating. Okay, so the first thing you need to do is make sure you have your graphic organizer. Okay, this is an awesome video. I'm really excited to teach it to you, but you do need to take some notes as you're watching the video. So make sure you have the graphic organizer, and it says evolution. How is that a fossil? And once you have that graphic organizer, it's a paper, it has a woolly mammoth on the front, very similar to these guys. Then you can get ready. If you do not, please pause the video here. Okay, awesome. So what I want you to do right now is discuss with your table group is what is a fossil? And also, what are some examples of fossils that archaeologists might find during a dig? Again, whenever you get to a question, please pause the video because I'm going to streamline and keep going forward. And also, if you need to rewind and listen to the question again, you can do that. So talk with your table group, what is a fossil and what are some examples of fossils and archaeologists might find during a dig? Okay, so a fossil is solid remains or imprints of things from the past. What are examples of fossils an archaeologist might find during a dig? Well, let's discuss. We can think about our card sorting activity, and we talked about different types of fossils like trace fossils. So you might find a movement that or footprints that an organism was doing at the time. You might find a cast fossil. You might find a full body fossil. Okay, so almost everything's intact, like the Iceman, right? Or a woolly mammoth preserved. So there's tons of different types of fossils you can find, from bacteria to living to mammals to plants, different types of organisms. Okay. All right, so as we go through, you are going to fill in the blank as I click on the screen. Okay, so your first set is, it says, what do you need to know on your paper? And then it says fossils. And you need to write fossils in that first opening. So fossils are solidified remains or imprints of once living organisms. So they're solidified remains or imprints. So if we look at all these fossils down here, these are all showing remains, okay? But we can also see imprints as well. The older the fossil is, down the rock layer it is. So these guys are going to be much older than these fossils up top. Organisms that resemble living creatures of today are mostly found in the top layers, so right up here. And we really recognize those, okay? We have these conch shells and clam shells that we eat if you go to a seafood restaurant, while the more ancestral forms are found in the lower layers. So these are definitely more ancestral. You can see this conch shell has some spikes on it. Now, we do have similar shells to that today, but you can see how they've evolved over time. Again, if that went too fast for you, please pause the video and go back and make sure you get in all of those blanks. Okay, so the next part are most fossils are found in sedimentary rock, although they can be found in different types of substrates. So we talked about the rock cycle class. We talked about the different types of rocks. So sedimentary, metamorphic, igneous, and we discussed why sedimentary is the best platform for fossils to be preserved, right? Because it's not too hot, the pressure's not too intense, it's not super new, and they can slowly layer over time. All right, so now the second, it says, whoa, dude, did you know? All right, so check that out. Most all organisms that have ever lived, 99% of them are extinct. Boom, mind blown, right? So fossils provide a historical sequence of life known as the geological timescale. So basically what I'm trying to get out here as you're filling in your blanks is that, oh, nope, is that I want you to understand that there's evidence for all of these geological times that we've come up with. So Cambrian all the way to now, right? And then the future. So understanding that we have evidence based off of different types of dating that we're going to get into. So absolute dating, relative dating, to show that this geological timescale is pretty accurate. Okay, so now you're on the second half of your front side of the page, and it says radioactive dating, and it starts with, we can estimate the age of a fossil using radioactive dating. Woo! So make sure you write that in there. So rocks contain radioactive chemicals that break down. The half-life is the amount of time it takes for half of the chemicals in a rock to decay or turn into another chemical. Whoa, mouthful, that was huge. So the next slide is going to be very helpful on explaining and understanding what this really means. So a half-life is the time it takes for half of the chemicals to totally decay. So we can analyze a sample of a radioactive chemical from a rock found near a fossil, calculate its half-life, and estimate how old the fossil is. So for example, we have this little woolly mammoth here, and we probably have a rock right next to it, okay? So we can check out the half-life of this rock, so these little carbon-14 are going away, and we can see how many carbon-14 are left, or if there's none left, how many of this new chemical are in there, so this nitrogen. All right, so we're a little bit down, so we're about halfway down that next section. It starts with different chemicals have half-lives, okay? So different chemicals have half-lives. For example, we're going to use carbon-14. So let's just focus on this little diagram up here. So we have carbon-14, and carbon-14 is a radioactive element, meaning that it's an unstable substance, so it can break down over time. So as carbon-14 decays, the atoms change to one another that are to a more stable element called nitrogen, right here. So if we look at carbon, and it's going to decay over time, and it's going to slowly start turning into nitrogen because nitrogen's way more stable and it's happy there. So it takes about 5,700 years for half of the radioactive atoms in a sample of carbon to change to a stable nitrogen. So it takes 5,700 years for half of these carbons to turn into nitrogen. So you're going to get about this. This is really helpful because this is our known, and this is our period of time that is known as our half-life. So we know that carbon has this half-life of 5,700 years. Uranium has a much larger half-life, so 713 million years. It takes for it to turn into lead, which is more stable than uranium-235. Thorium, okay, much even bigger than uranium. And then we get to plutonium, 2 million years, so a little bit less than these other ones, okay, and for half of it to turn into this other element. So we really like to use carbon because it's a little bit less time, but if we want to look at other rocks, maybe some other rocks have different elements in them, so we can know these elements for those. Okay, so how does this all work? You guys are probably like, what? What is going on? So at the very bottom of your page, you have one new little tick, and it says all living things. So start there. So all living things contain carbon-14. Which is awesome. So that really helps us out when we're doing this radioactive dating. So why is this? Because plants take in carbon dioxide. So let's say there's all these plants around here, and this animal is going to eat those plants. But before that, these plants have to grow. So how do these plants take in carbon dioxide? Boom, you got it, photosynthesis. And therefore, they also take in carbon-14. So they're taking carbon dioxide, so they're taking an isotope, so they're taking this carbon-14 in. So all these plants are taking in carbon-14. Then this animal is going to start eating all those little plants. Eat, much. The carbon-14 is then transferred into the belly of those animals and then transferred throughout their bodies. Okay, and when that plant or animal dies, oh, so sad, dies, they're no longer taking in carbon. Sweet, though, that's cool. Because then that carbon inside of them starts to decay and turn into nitrogen, which is the more stable thing. So after a while, most of that carbon-14 will decay and turn into nitrogen. So all of these plants here go through photosynthesis, taking in all that carbon. Those animals eat those plants, and they have that carbon inside of them, and they're not taking any more carbon in. And then they die, and that carbon starts to decay and turn into nitrogen. All right? Okay. So now we're going to practice this idea. So go ahead and turn your papers over, and you're going to see a couple boxes here. You have 0 through 5. So there's technically 6 boxes, but we label them 0, 1, 2, 3, 4, 5. So as you look at them, and you're definitely going to need to pause during this part so you can do the activity, what you're going to do is you're going to draw 100 dots. 100 dots. Yes, I said 100 in box 0. This represents the amount of carbon-14 in the sample when the organisms die. So we're going to say at the time of death is 0. So box 0 is when the animal died. So we have these woolly mammoths, they're roaming around, and bye-bye, they all died. Oh, so sad. So now in box 0, please draw 100 dots. Pause the video. Okay, now that you've drawn 100 dots, we're now going to move on to box 1. So box 1, we're going to pretend that 5,700 years have passed. Whew. So how many dots should I have left? So remember, we started with 100, and now this is our half-life. How many dots or carbons do we have left? Pause the video and go ahead and start drawing those dots. All right, if you said 50 dots, you are correct. Boom, 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 boom. Winner, winner. So, half-life, 50 dots. Okay, so now on to the next, and remember, so 50, so half of 100 is 50, so that's their half-life, okay? And we're just saying 5,700 because half of carbon are left after those years. Okay, so now what would happen to box 1? So we're thinking about box 1. If another 5,700 years passed, would all the dots be gone? Okay, so I want you to draw the new amount of dots in box 2. Okay. No. Okay, so you were correct if you put 25 dots. Woohoo! Yeah, awesome job. So, we have about 25 dots. So now you're going to continue drawing the new amount of dots in each box after the half-life has passed. So go ahead and pause the video, and I want you to fill in box 3, 4, and 5. Okay, so remember, you're answering all these questions underneath the boxes as well, right? So you want to continue answering these, and I don't know if I made that clear earlier. So make sure you answered 1, 2, and 3 on your paper. Okay, so now we're on number 4. So another 5,700 years have passed. Box 3, how much carbon-14 would be left? Well, you should have just done this. So we said 12.5 dots remain. You are correct if you got that. Okay, so now if something died 5,700 years ago, how much of a percentage is left now? So let's forget about the boxes right now and step back and think about if something died 5,700 years ago, how much of a percentage is left of that carbon-14? Pause the video if you need. You were right if you said 50% of the sample remains. Awesome. Okay, what if it's been 11,400 years? How much is left? Pause the video if you need to. All right, you were right if you said 25% of the sample remains. So if we think about 11,400 divided by 2 is 5,700. So we're just breaking it in half every time. So we start with a full organism with all the carbons, and then only 50% of the carbon is left. And then only 25% of the carbon is left. So now if we think about 17,100 years, how much is left? Pause the video and write your answer. All right, you were correct if you said 12.5% of the sample remains. So again, cut it in half again. All right, so if you need to go back through, go ahead and go back through that piece of the video. And you can also work with your group now if this is, if you want some extra help. So number 8, using boxes 0 through 5. So go back to the boxes. Okay, how many total years have passed since this organism has died? So you're going to have to do a little bit of math here. You want to think about how many half-lives there are and how many years it takes for each half-life to occur. Pause the video. All right, so you should have written your equation, and you would be correct if you had this equation. So there was 5 half-lives, because remember 0 was when they initially died, so it only broke down 5 more times, and each of those boxes represents 5,700 years. So you multiply those together and you get 28,500 years since death. Woohoo! That's a long time ago. All right, now the last question, and then we'll just have one last slide to wrap everything up. What would be the amount left if another 5,700 years passed after box 5, so box 6 really, so if we had another box 6, what would be the amount left if there was another box? And you can do a percentage here. You don't have to do dots. All right, you should have paused the video. And your answer should have been 1.5625% of the sample remains. Boom. Okay, so again, if you just go back through and you divide each of those in half each time, you're going to get this for your 6th box. All righty, awesome. Great job. Give yourself a pat on the back. That was a lot of calculations in math. So what I want to end on here is notice how after a little while, it becomes so small that we can hardly even see it anymore. So when you're making all of these little boxes or these little dots, they get so tiny and you barely have anything left. So that is the point at which carbon dating is no longer useful, and that happens a lot. So we need to find something with a longer half-life to date older things. And those were some of those examples earlier, like uranium, plutonium. We use ones with very long half-lives to date the Earth. Okay, so I hope you learned a lot from this slideshow. Hopefully you got everything filled out. And if you're all done, you can go back through, really make sure you understand all of this. And make sure you hold on to that worksheet. If your teacher tells you to turn it in. If they ask you to hold on to it, hold on to it. For my class, I would like you to turn it into the basket. Okay, so have a great rest of your stations. And again, if you are done now, you may work on vocabulary or any other stations you didn't get to finish.